So hi students, up to this class we discussed about the collector coupled monostable multivibrator and at the same time what is the designing process of the collector coupled monostable multivibrator. So in this session we discussed about what is meant by emitter coupled monostable multivibrator and what is the purpose of that particular emitter coupled monostable multivibrator. Simply we can say that what is the emitter coupled monostable multivibrator. So emitter coupled monostable multivibrator nothing but it consisting of two transistors as like collector coupled monostable multivibrator. But the difference between these two is simply we can say that in emitter coupled monostable multivibrator, so there is no feedback occurred here. Simply we can say that in emitter coupled monostable multivibrator, so we don't have feedback. So we don't have feedback. So here, so that is the feedback will be missed here. Simply we have to say that the feedback nothing but so the transistor Q2 that is in this particular time. So the output of this transistor is connected at the input of transistor Q1. But here this concept will be missed. Simply we have to say that so for emitter coupled monostable multivibrator the feedback connection will be missed. At the same time we can say that here so the both emitter terminals will be connected with the resistor RE. So this one provides the feedback simply. So that coming for the circuit diagram point of view, we can say that in the initial condition transistor Q1 nothing but the output of this transistor is connected to the input of transistor Q2, but the output of Q2 is not connected to the input of Q1. Here both the emitter terminals will be connected to a resistor R. So that is the difference between these two things, and at the same time so what is the voltage of this particular base emitter junction? Simply we have to say that we give some of the input signal here, so that the input signal will be a pulse signal. So we give the input signal here. So based upon that, conditions will be changes. So in the initial condition, we assume like the transistor Q1 is in off condition and Q2 is on condition. So that is it is in the stable state. Simply we assume like that. That is transistor Q1 is in off condition and Q2 is in on condition. So in this time, what happens? What is the condition? Just check the condition. So during this time, so obviously here the voltage that will be VEN, the emitter and base junction voltage. So that is VB1, base emitter 1 is less than VEN plus V gamma. Obviously the V gamma voltage is the cut-in voltage for the transistor, and at the same time what is the VEN? That will be the emitter junction, that is the emitter voltage. Simply we have to say it as VE. So the input voltage will be less than this condition. Obviously the transistor Q1 is in off condition and Q2 will be on condition. So actually for changing of the stable state to quasi-stable state, we go for the triggering pulse. So for collector coupled monostable or collector coupled bistable multivibrator, we apply a negative triggering pulse. But coming for this particular thing, we apply a different triggering pulse. So that will be a positive triggering pulse. So for changing of this state, that is this state is known as stable state. So for changing of this state, we obviously apply, so that signal will be positive triggering pulse. So that is a major important thing, positive triggering pulse. This positive triggering pulse is applied to the base of transistor Q1. So then obviously transistor Q1 goes to on condition. So why? Because the input voltage is here, the positive triggering voltage is greater than VE plus V gamma. So during this time, so obviously transistor Q1 goes to on condition. So when transistor Q1 goes to on condition, so this signal, that is here the voltage will be, what is the collector voltage? Simply the collector voltage will be VCE SAT. So this VCE SAT voltage is given to the base of transistor Q2. So then Q2 becomes off condition. But during this time what happens? So in this time this particular, that is this capacitor starts doing discharging. Why? Because it is connected in between VC sat and nothing but another terminal. During this time the capacitor starts discharging. When capacitor starts discharging, what is meant by that? Simply it produces nothing but it releases the voltage. So when capacitor releases the voltage, when it reaches the VE, nothing but VE plus V gamma level, so then obviously the transistor Q2 goes to on condition. So again the transistor Q1 goes to off condition. So that is a major thing about the emitter coupled monostable multivibrator. So this will be the operation of the emitter coupled monostable multivibrator. So I am coming for the next one. So that is what is the waveforms of this particular thing. Simply we have to say that so emitter coupled monostable multivibrator waveform. So first one, the input signal in the initial condition, we assume like that transistor Q1 is in off condition and Q2 will be in on condition. And at the next time Q1 goes to, that is in active region. When it goes to active region, the voltage will be generally, so here the voltage we have to represent with the VCC, and so this voltage is at the second transistor collector terminal. So this waveform will be absorbed at the second transistor collector terminal. Simply when transistor Q2 becomes on condition, this voltage will be VCE sat, and it reaches next one when Q2 goes to off condition, this voltage will be VCC. After that it goes to the VCE sat. So but here there is a capacitor in between these two things. So in between these two things, so there is a capacitor here. So this capacitor provides so that means this capacitor provides charging and discharging. So that's why the waveforms will be changed. Simply we have to say that that will be like this. So the waveform will be like this, and at this condition the reverse process will be there. That is at transistor Q1 the initial voltage will be VCC. After that this voltage when transistor Q1 goes to active region, the voltage will be VCE sat, and finally it goes to the VCC again, nothing but it goes to off condition. And the next one is VBE2. So VBN2 nothing but initially transistor Q2 condition will be in the on condition. That's why the input voltage will be generally VEN plus V gamma. After that it decreases. So when we apply a positive triggering pulse, so during this time it can be decreases. So then what happens? Simply we have to say that the voltage will be, so it will be decreases, then the voltage will be increases. So nothing but the waveform will be increases, and this waveform will be reversed for that. So this is the waveforms of the emitter coupled monostable multivibrator. So up to this we discuss about the monostable multivibrator. Simply monostable multivibrator nothing but, so it consisting of one stable state and one quasi-stable state. For changing of stable state to quasi-stable state, obviously we have to give, so that is a triggering pulse. So this triggering pulse will be a negative triggering pulse. This negative triggering pulse will be applied at the off transistor collector terminal as well as on transistor base terminal. So this is that is our choice. Most of the cases we applied a triggering pulse at the off transistor collector terminal. At the same time we have to say that the monostable multivibrator is also known as one shot or single shot. So monostable multivibrator, another name of the monostable multivibrator is known as single shot or one shot. At the same time the major application of this monostable multivibrator is pulse generator. Simply these type of monostable multivibrators are mostly used in the pulse generation, and it can be also be known as voltage to time converter. So the major application of this coming for monostable multivibrator is voltage to time converter. And next one is astable multivibrator. What is meant by next thing, that is what is meant by astable multivibrator. So nothing but astable, nothing but it does not contains any stable state. Here there is two quasi-stable states will be there. So that is Q1 will be on condition at the initial stage, we assume like that, and Q2 will be off condition. After some time it goes to that is Q1 goes to off condition and Q2 goes to on condition. After predetermined times it goes to the previous session. So that is the difference between the monostable, astable and bistable. Simply we can say that these astable multivibrator does not contain any stable state. Here both states will be a quasi-stable states only. So quasi-stable state nothing but without any triggering pulse it moves to one state to the another state. So that is a major thing about this. Nothing but this astable multivibrator is also known as pulse, nothing but square wave generator. Why? Because so without any triggering pulse it changes the state of the signal. So without triggering it moves to one state to another state, nothing but the output will be, so we have to take the output at the collector of transistor Q1 or collector of transistor Q2. So the output will be obviously square wave pulse. So nothing but it is transition between VCC2 and VCSat. So obviously the output will be a square wave pulse. So that's why astable multivibrator is also known as square wave generator. So simply we have to say that the astable multivibrator is also known as square wave generator. And coming for that astable multivibrator, so here the coupling elements will be a capacitive coupling. Why? Because for using of quasi-stable state we use a capacitive coupling. So that's why we go for the capacitive coupling for this type of multivibrator. So let's check the condition of the astable multivibrator. Again like monostable multivibrator and bistable multivibrator. Astable multivibrator also divided into two types, that is collector coupled astable multivibrator and emitter coupled astable multivibrator. First we discuss about the operation of the collector coupled astable multivibrator. So let us check the operation of this particular collector coupled astable multivibrator. Simply we have to say that, so here also it consisting of the two transistors. So let us I have to redraw this diagram. Both the emitter terminals will be connected to the ground and both the collector terminals will be connected to the VCC through RC1 and RC2 through VCC. After that, so here the coupling element, what is meant by coupling? The output of one transistor is connected for the input of another transistor. So this type of connection is known as simply coupling. So here that is capacitor C1. The output of this one is connected to the transistor Q2 and this one will be connected to the transistor Q2 collector terminal. Simply we have to say that the output of Q2 will be connected to the Q1 base through capacitor C1, C2 and C1, and this resistor will be known as R1 and R2. So this is about the diagram of the astable multivibrator. So based upon that we have to check the operation of the astable multivibrator, how we can produce the square wave pulses. Let us check. So in the initial condition we assume like that the transistor Q1 is in off condition and Q2 will be on condition. That is our assumption. So that is in the initial state we assume like the transistor Q1 is in off condition and Q2 will be on condition. So during this time what is the voltage? Simply these will be known as VA and this will be known as VB and this one is VC and this one is VD. So what is the voltage of that? VA, VB, VC and VD. What is the VA? So transistor Q1 is in off condition. Obviously the VA voltage is less than VB sat. We assume like that it is a negative voltage. And what is the VB? When transistor Q2 goes to on condition, obviously the voltage will be greater than VB sat. Simply we have to say it as VB is equal to VBE saturation. And next one is VC. So that one will be transistor Q1 goes to on condition. So what is the off condition? What is this VC value? VC nothing but VCC. Why? Because Q1 is in off condition. So that's why the collector voltage will be VCC. And the VD will be VD nothing but VCE saturation. So in this time what happens? We have to check. So in this time the particular transistors, capacitor C1 starts charging. Why? Because these will be connected in between VCC and VBE sat. So during this time the capacitor C1 starts charging. So what is the path for the charging? Simply the path will be like this. It charges in this way. So VCC and RC1. After that it gives to the capacitor C1 and another terminal will be connected So simply the charging path of the capacitor will be like this. So here during this time the capacitor C1 starts charging. At the same time, what is the condition of C2? C2 is connected in between VC sat and so that is negative. So during this time the capacitor C2 starts discharging in the path of, so like this, the path will be like this, R2 and this VCC, and this one is a capacitor and this one is connected to the VD, another terminal will be connected to the V. So the discharging path will be like this. So this one will be, so C2 and this one will be C1. So that is when transistor Q1 goes to off condition and Q2 goes to on condition, in this particular time the capacitor C1 starts charging. The charging path will be like this through RC1 and like this up to VBE sat. And during this time, at the same time, the transistor C2 starts discharging. Why? Because so in this particular time the C2 is connected in between VCE sat and negative voltage. So in this particular time capacitor C2 starts discharging. So in this manner, so while the capacitor starts C2 starts discharging, what happens? So when any capacitor starts discharging, it means it releases the voltage. So the output of this C2 will be connected, the one terminal will be connected at the, so VC sat, another terminal will be connected, that is VD, another terminal will be connected to VA. So nothing but it releases the voltage. When the capacitor releases the voltage, when this voltage is given to the VA. So that is when VA voltage is reached at the VBE saturation, then obviously Q1 goes to on condition and Q2 goes to off condition. So that is the thing of this particular one. Simply we have to assume that first one transistor is in on condition, another one goes to off condition. So during this time one of the capacitor starts charging, another one goes to discharging. So that is in this particular time the capacitor C2 start discharging. When this capacitor C2 start discharging, in this particular time it releases the voltage. This release voltage is given to the transistor, so Q1 base terminal. Transistor Q1 base terminal, nothing but, so when it reaches the VBE saturation voltage, that is VA reaches the VBE saturation voltage, then Q1 goes to on condition and Q2 goes to off condition. So in this particular time, and what happens, what is the output condition? Let us check the condition. So that is when Q1 goes to on condition and Q2 goes to off condition, simply we have to say that the VA voltage is VBE saturation and VB is a negative, and what is the VC? VC nothing but Q2 is non condition. When transistor Q1 goes to on condition, the collector voltage will be VCE saturation, and next one is VD. So VD nothing but Q2 goes to off condition, that is VD is equal to VCC. So in this particular time again what happens? So here we don't apply any triggering pulse. Without triggering pulse it moves one state to another state. So that is a great thing about Astable Multivibrator. So by the capacitive coupling. So simply in this time what happens, in this particular time the capacitor C1 starts discharging and C2 starts charging. Why? Because C2 is connected in between this VD and VA. So VD voltage nothing but VCC and VA voltage is nothing but VBE saturation. In this particular time the capacitor C2 starts charging, that is RC2 and C2. So the charging path will be like this. So in this particular time the capacitor C2 starts charging. At the same time what is the condition of C1? So the C1 starts discharging. So like this, the discharging path will be R1 and VCC, and this one is given to the capacitor C1. So like this. So the another terminal will be connected to the VB. So in this particular time when C1 starts discharging, nothing but it releases the voltage. So when this voltage is given to the transistor Q2 base terminal, nothing but VB, when it reaches the particular point, obviously transistor Q2 goes to on condition. So this process will be continued up to infinite levels, so that it produces the square wave pulses. So this is the operation of the Astable Multivibrator. Nothing but Astable Multivibrator is simply square wave generator without any triggering pulse, it changed from one state to another state. So at the same time, at one of the transistor, that is one transistor is in on condition, another one goes to off condition. So off transistor side capacitor will be discharged and on transistor side capacitor will be, off transistor side capacitor will be charged and on transistor capacitor will be discharged. So that is a condition of the astable multivibrator. And let us check the waveforms of the astable multivibrator. Simply we have to say that, so first we have to take the output waveforms at the each base and collector terminal. So first we have to take at the transistor Q2 collector terminal. So the transistor Q2 at the initial stage we assume like that transistor Q2 is in off condition and Q1 is in on condition. So where transistor Q1 is in on condition and Q2 is in off condition, we have to take the output at Q2 collector terminal. So that's why this will be VCC. After that, without triggering pulse, it moves to the VCSat and VCC like this. So it produces square wave pulses. So at the same time, we observe output at the VBE2 also. That is transistor Q2 is in off condition. When transistor is in off condition, the base voltage will be negative. So this negative voltage, that is when it starts, that is the capacitor starts discharging. That means it gradually increases. So when it reaches a particular level, that is VBE saturation, obviously the transistor Q2 goes to on condition. Again it goes to off condition like this. So these waveforms will be reversed for that particular transistor Q1. Simply the Q1 waveforms will be like this. That is VC1 will be here when the transistor Q2 goes to VCC, it goes to VCSat. After that it goes to VCC and VCSat and like this. And in this particular time it will be like this. That is VBE sat and negative like this. So the waveforms of the VC1 and VBE saturation. So simply, so the total time here it produces pair wave pulses. So obviously the astable multivibrator also having two types, that is collector coupled, also two types, that is symmetrical square wave generator and asymmetrical square wave generator. So symmetrical square wave generator nothing but on time period, that is this VC time period and VCC nothing but same. And but coming for the asymmetrical, the on time period and off time period will be different. So it is majorly depends upon the components, that is resistor and capacitor. So obviously the capacitor values will be same, but the resistor values of R1 and R2, that is discharging path for the capacitor, is different. So due to this it produces asymmetrical square wave pulses. So that is a astable multivibrator. So let us check the frequency of oscillations of the astable multivibrator. So simply we have to say that what is the frequency of oscillations. So at this particular time, we have to say that the transistor, so Q2, that is Q2 goes to off condition. So it gradually increases to VBE saturation. So in this particular time, what is the condition, that is at T is equal to T2, we assume that is, so here the transistor Q2 goes to on-off condition. In this particular time, transistor Q2 goes to off condition. When transistor Q2 goes to off condition, so we have to say that is, so in this particular time the C2 starts discharging. So then the node B voltage, that is in this particular interval of time, the particular C2. So C2 nothing but this terminal, sorry C1. So in this diagram we have to replace like this. So in this particular interval of time, so C1 starts discharging and this resistor will be R1 resistor. So at this particular interval of time, so what happens, we have to check the condition like this. So it reaches the VB voltage increases gradually. Then what happens, from this diagram we have to check the condition. So we have to take it as that one will be R2 and C2. So that is our choice. So this one will be R2 and C2 and R1 and C1. So that is when this VB voltage is gradually increases. What is meant by VB voltage gradually increases? that is C2 starts discharging. For which condition I am taking like this simply. So I am taking T2 as my time period for this VB2, and that's why I have to change the R2 and R1 positions. That's the only thing. So simply we have to say that in this particular interval of time, so the C2 starts discharging. So once C2 starts discharging, we assume like that. So that is capacitor exponentially increases. So then what is our formula for VB? Capacitor charging and discharging. VB is equal to V final minus V initial into e power minus T by RC. What is the V final value? So actually it charges up to nothing but it discharges up to VCC. But so when it reaches the VB saturation, it goes to the on condition. But the discharging voltage V final is equal to VCC and V initial will be minus VCC. Just substitute the values here. That is VB is equal to, so VCC minus of VCC minus of VCC. Power minus T by RC. Simply we have to say that VB is equal to VCC minus 2 VCC into e power minus T by RC. So at T is equal to T2 condition, this VB voltage is generally reached to the V gamma level. That is at T is equal to T2. That is R2C2. These values will be R2C2. Why? Because transistor, that is capacitor C2 start discharging. Due to this discharging only, it exponentially increases. So that is at T is equal to T2. VB is equal to V gamma, which is equal to 0. So then VCC is equal to 2 VCC into e power minus T by RC. And VCC will be cancelled, and e power minus T2 by RC, sorry, at T is equal to T2, we have to take this one, and T2 by R2 into C2, that is this thing will be 1 by 2, and e power minus T2 by R2 C2 is equal to ln of 1 by 2, and T2 of R2 C2 is equal to ln of 1 by 2. So that is minus 0.693 R2 693 minus will be cancelled. That is T2 is equal to 0.693 R2 into C. So that is a condition at base of transistor Q2. At next condition, that is at base of transistor Q1, that is at time is equal to T1 condition. What happens in this particular time? The capacitor C1 starts discharging. Simply we have to say that this equation will be like this, but in place of R1 and R and C, we have to substitute the R1 and C1. At T is equal to T1, the value will be 0. As like that, the VF is equal to VCC, and this one will be saved. Here R1 and C1, and this one will be VE. At T is equal to T1, VA will be V gamma, which is equal to 0. That is T1, R1, C1 is equal to 1 by 2, and e power minus T1 R1 C1 is equal to, so that is e power, that is simply we have to say that 1 by 2 minus T1 R1 C1 is equal to ln of 1 by 2, which is equal to minus T1 R1 C1 is equal to ln of 1 by 2, nothing but minus 0.693, minus will be cancelled. T1 is equal to 0.693 into R1 C1. So this is about the two different conditions. Actually for monostable multivibrator, there is only one capacitor which charges and discharges, but in this particular time we have to use the two capacitor. So it produces the time period, that is T1 is equal to 0.693 R1 C1 at particular time, and for T2 condition also it produces the same time interval. And for symmetrical square wave, what happens and what is the output? So for this particular condition we assume like this, that is for asymmetrical square wave, so that is T1 is not equal to T2, so then what is the output? So that frequency of oscillations and total time period T is equal to 0.693 R1 C1, and 0.693 R2 and C2. But at T is equal to T1, or simply we have to say that R1 C1 is equal to R2 C2. So in this particular of time, total time T is equal to T1 plus T2. So in place of R1 C1, we have to replace this particular thing with RC. So let us rewrite this. 0.693 RC plus 0.693 RC. So which is equal to 1.386 RC. So this is the total oscillation, that is T is equal to 1.386 RC for pulse width of the astable multivibrator. For this is for symmetrical square wave and this is for the asymmetrical square. So this is about the astable multivibrator pulse width calculation, and next we discuss about the application of the astable multivibrator. Simply the major application of the astable multivibrator is, this is used as voltage to frequency converter. So monostable multivibrator can be used as a voltage to time converter. How it can be acts as voltage to frequency converter. So let us check. So the previous thing will be same, but the only difference will be here the V final condition will be V and V initial condition will be as usual. So let us take the condition, that is at T is equal to T2. So V final is equal to V final minus V initial into e power minus T by R. As usual here V final is equal to V and V initial is equal to minus VCC. Just in place of V final we have to substitute the VB value. So that is, what is the V final? That is V minus of V minus of minus VCC, that is plus VCC into e power minus T2 by R2 into C2. So at T is equal to, that is at T is equal to T2, VB is equal to 0. V minus of V plus VCC into e power minus T2 by R2 into C2. So that is V plus VCC into e power minus T2 by R2 into C2 is equal to V, and e power minus T2 R2 into C2 is equal to V by V plus VCC. So just we have to check the condition of the e power, that is minus T2 R2 into C2 is equal to ln of V plus VCC. So from this we have to check the condition, that is ln of V plus V by VCC, which is equal to, that is minus T2 is equal to ln of V by V plus VCC, and what is the next positive value? T2 by R2 into C2, which is equal to ln of V plus VCC by V, and T2 is equal to, so that is ln of V plus VCC by V into R2 into C2. So for this R1 and C1, that is for V also same waveform will be produced. For in this place the T1 will be like this. The T1 is equal to ln of V plus VCC by V into R1 into C1. So that is at T is equal to T1 and at T is equal to T2 we get this waveform. So finally we get we produce the T, that is T is equal to, what is the T? T1 plus T2 on time period plus off time period. What is the on time period? That is ln of V plus VCC by V into R1 C1 plus ln of V plus VCC by V into R2 C2, and frequency will be F is equal to, 1 by ln of V plus VCC by V into R1 C1 plus ln of V plus VCC by V into R2 C2 for asymmetrical square wave. For this particular thing is occurred for the asymmetrical square wave. For symmetrical square wave, what happens? Simply we have to say that R1 C1 is equal to R2 C2. So that's why the output will be like this. That is T is equal to 2RC. That is RC will be same 2RC ln of V plus VCC VCC by V. And what is the frequency? That is 1 by 2 RC into ln of V plus VCC by V. So simply we have to say that so the output voltage, here the VCC value will be constant and RMC values will be constant. Here the output change, that is the V changes will be changed. This Astable multivibrator is known as voltage to frequency converter. So with any change of voltage at this input side will occur output to frequency change. So this is about the Astable multivibrator as voltage to frequency converter. And next one is the design process of Astable multivibrator. So what is meant by designing? Simply we have to say that for designing we have to tell that we produce the, we give the VCC value and HFE and what is the current, they give these values. We have to design this particular multivibrator, nothing but we have to find this resistor and capacitor values. So based upon that we get that output. So for designing of Astable multivibrator we have two processes, that is asymmetrical square wave generation and symmetrical square wave generation. So in the next class we discuss about the design of this particular Astable multivibrator. Thank you.